Welcome to Pre-Calculus Notes for Essential Skill C1, Operations with Exponents and Logarithms. In this section, we'll mainly review how to deal with interesting exponents and some basic log rules. The first thing we should do is make sure you remember all the properties of exponents. Please pause the video and try these out, and then I'll give you the answers. Here we go. When we multiply with the same base, we add the exponents. When we divide with the same base, we subtract the exponents. When we raise a power to a power, we multiply the exponents. When we raise a product to a power, we distribute the exponent. When we raise a quotient to a power, we distribute the exponent. Anything to the zero power is 1. Anything to a negative power is a reciprocal. Anything to a fractional power is a root. The denominator is the order of root that we're taking. One rule that we don't have is distribution over addition. It doesn't work. If we evaluate, 2 plus 1 is 3, 3 cubed is 27. That is not equal to 8 plus 1. Similarly, radicals, which are exponents in disguise, remember that they are the 1/2 power. The square root of 25 minus 16 is the square root of 9. That is not equal to 5 minus 4. Next, let's look at some simplification exercises. For the first expression, we see an example of where we can go horribly, horribly wrong. We cannot distribute that minus 2 to the negative 3 or negative 1. We just saw that exponents don't distribute. So instead, we have to evaluate what's in the parentheses first. For example B, we're going to look at the very useful technique of rewriting in terms of a lower base. 8 is 2 cubed. Now we have power to a power, so 3 times 2/3 is 2. 4 times negative 3/4 is negative 3. The rest are just different ways of using these rules. This would be a good place to pause the video and try out the next 4 examples. Here are my solutions. Next, we look at logs. Much of what we're going to try to do involves alternating between logarithmic form and exponential form. One will usually be a better way to solve a problem. Our cardinal rule is that the log is equal to an exponent. Y is the log. It is the exponent in exponential form. We have special bases. If no base is specified, we use base 10. That's called a common log. Ln is the natural log. That's log with a base of e. E is an irrational number that's approximately equal to 2.7. Two of the properties we're going to use are based on the fact that exponential functions and logarithmic functions are one-to-one. We're going to call these the one-to-one properties. What they say is that if the outputs are the same, then the inputs must be the same. If you think about it, you can probably reason out why that would be true of any one-to-one function. Several of these are straight off the mastery test, so I'll bet you can come up with the answers to a lot of these on your own. Here are my solutions. For part B, I like to set this equal to x. We can use the base changing trick. We'll put this in exponential form, and then rewrite both in terms of a base of 3. Now we use the one-to-one property to finish up. Here we're going to use the base trick again. On the next problem, I believe we have a typo. I think without a calculator this is going to be hard to do, unless we change the base to 3. For example f, we're going to have to write this in terms of rational exponents first. Recall that natural log and e to a power are inverses of each other. And so, essentially, they'll make each other go away. Our answer is going to be negative 2/3, but let's see why. If we set this equal to x, recall that natural log is log base e. So we get e to the x equals e to the negative 2/3. So x will be negative 2/3. Part G, you can simply reason out using language. The log is the exponent. So what power can we raise 7 to get 7 to the 53rd? Obviously 53. Log base 2 of 32 is 5, and 2 to the 5th is 32. This suggests a flip side of another log rule that we'll see a little bit later. Next, we look at domain and range. We're going to explore domain and range by making a table of values. First, we'll see if positive 0 or negative x's work. So yes. Next, we'll look at the y's. Did we get any positive y's? Yes. Did we get any y's equal to 0? Can we get any y's equal to 0? Well, we can try some other numbers. It seems clear that we're never going to reach 0. We cannot get a 0 for a y value. By the same reasoning, we will never find an exponent that will lead to a negative result. This suggests that the domain is all real numbers. The range seems to only be y greater than 0. Let's try the same thing with logs. Log base 2 of negative 1. Well, what power can we raise 2 to get negative 1? Well, we just saw that we can't. What power can we raise 2 to get 0? Again, we saw that it can't be done. What power can we raise 2 to get 1? Well, 0. So right away it becomes clear that negative x's are not allowed and 0 is not allowed. Positive numbers seem to work though. We also saw that we can get a y equal to 0. Can we get a y that's greater than 0? Sure, if we plug in x equals 2. Log base 2 of 2 is 1. Can we get a negative number? Yes. Log base 2 of 1/2, well, 2 to the negative 1 is 1/2. So now our domain is restricted, but our range is not. It may have already occurred to you that this fits in with our theme for inverse functions. Exponential and log functions are inverses of each other. Our theme for inverses was we switch x and y. Well, the legal x's became the legal y's. The domain for an exponential function became the range of the log function. Now we look at how to apply this. We know the rule for domain of log functions, and so we're going to solve it. We know that the input of the log function must be greater than 0. So we're going to set up an inequality and solve it. Again, the input must be greater than 0. Notice that this has a lot of similarities with skill A6 when we found domains dealing with radicals. Here's an example where we're going to have to go to the number line. This is a nonlinear function, and so we have to do a full analysis of it. To get our critical points, we'll see what happens when we set this equal to 0. If we put this polynomial into factored form, we can use our shortcuts. We can test a very high number, 10,000. It'll be positive times positive, giving us positive. X minus 3 has a multiplicity of 1, and so we can flip the signs. And same with -2. So if we want where it's greater than 0, our solution is going to omit the critical points and highlight the positive regions. Our domain You may also use interval notation if you've gotten used to that. Try this last one on your own and see how you do. First, we need to state that our input is positive. We can either factor when we find critical points, or we can factor now. We can read the critical points right out of the factored form and build our number line. Again, we're looking for where we are strictly greater than 0, so we will omit the critical points. We can use our shortcut by testing a very large number. We'll have a positive number times 2 minus 10,000, which is a very negative number. And so our rightmost interval will be negative. Our multiplicities are both 1, so we alternate. Finally, we're going to look at using these properties to solve equations. Our primary technique is to solve for the exponential expression and then raise to the reciprocal power. The reciprocal of 1/2 is 2, so we raise both sides to the second power. Power to a power multiplies, so this eliminates the exponent. And then our equation becomes simple. When you look at example 6a, bear in mind that an exponent will not distribute over addition. We need to isolate the exponential term first. Go ahead and try these. When we have a logarithmic equation, we simply rewrite in exponential form. Then we apply the same technique. I'm going to skip to example C so that I can leave B and D for you to try. We're still going to use exponential form. So 2 to the first power equals the input of that log. Now we use exponential form a second time and solve. Pause the video and try B and D. Here are my solutions.